All right, so this note here about international students signing up, there are several international students taking the class remotely. And so I'm just putting that on here too for them as a reminder. I've been emailing them with the details, but hopefully I know most of them are watching the videos, and hopefully they'll just see this and be reminded they need to sign up for one of those times if they're not going to come to the regular class time. This group, second period, actually, we don't have any of those students in this section, but I often record your class, so they are getting to know some of you through video, even though they're not going to be in your class whenever we get back on campus. Sounds like the goal is January 6th when we come back second semester, so be nice to have everybody back on campus if that works out. All right, so for the breakout rooms, I'm going to have you get into groups, work on worksheet 3. When you come back from the breakouts, then I will have you teach your question, and I will go over the last 3. And like I said, then we'll just review. When you come back, make sure you have a way to visually share the question that you're assigned, as we've done before. Make sure everybody in your group shares in some way in the teaching process, so that you're dividing up the work and having multiple people share. And I think we've done this a few times now, so hopefully that's clear. We'll have group 1 do problem 1, group 2 do problem 2, group 3, and 4, so just straightforward today. Your group number will be the problem number you're assigned. Any questions? All right. All right, I think everybody's back in the main classroom. Let's have group 1 walk us through problem 1.
All right, hang on, let me just get the screen share up. There we go.
Can you zoom in a bit, Ethan?
Yeah, let me try.
Okay. Okay, so for the first part, so we have the angle, which is 50 degrees, the length away, which is 24 meters, and then the initial velocity, which is 18, which is going to the, and then we're trying to find dy. So for the first part, you use d equals v times t, and you'll get, and you put in 24 meters equals, oh wait, I forgot one part, which is vx, which is 11.6, and vy, which is 13.8. So you plug in 24 meters equals 11.6 meters per second times t, which is 2.07 seconds. And then you have dy equals vy times t, 1/2 at squared, which you plug in 13.8 meters per second for the vertical velocity, and then 2.07 seconds, 1/2 negative 9.8 meters per second squared times 2.07 squared. And then you get your height, which is 7.55 meters, but you can round it to 7.5.
And I just realized I forgot to put seconds on that 2.07 squared. There should be a seconds inside the parentheses. All right.
Okay, so then for B, we're trying to figure out how far the balloon would go if the building wasn't there. So we're kind of doing the same thing that we did on the projectile motion simulation. So you use Vy equals negative Vy initial. So then you just plug in from there, from the previous equation, we got negative 13.8 meters per second for the final velocity if the building was there. And then it equals 13.9 minus negative 0.8 meters per second, or negative 0.81 meters per second squared, which is the acceleration due to gravity, and then times time. And then once you simplify that, it comes out to 2.82 seconds. And then, like I said, we do the equation that we used on the projectile motion simulation, just dx equals velocity of x initial times time. And then once you plug that in with 11.6, which we found earlier, meters per second times 2.82 seconds, you get a final position of 32.7 meters, and then you can round to 33 meters if you want to, which is the answer that was on the last page.
Before
and
we
then
go
for
on
the
to
fin-
C, quick question is, you've got on the first side there, the negative 13.8 meters per second equals negative or equals 13.9. Is that, are those
Oh.
supposed to both be 13.8?
Yeah, that's probably,
Okay.
yeah, that's just a
A
typo. that
handwritten
was writing.
typo. Yeah, I just was making sure there, in case anyone else is confused, those should be the same, right? Just opposite signs. Okay, good.
All right, and then for the last one, this was if it's launched from less, there's another point because it's not 45 degrees where it will hit the wall at the same point. So we had to figure that out. So I took our second kinematics equation and put in the height on the wall, which was 7.55 meters. We found that in the first problem. And then the vertical velocity, which was 13.8 meters per second times t plus 1/2 negative 9.81 meters per second squared times time squared. And then if you FOIL that all out and get it all on one side, then you can factor it. And when it's factored, then you have two solutions. One of them is 2.07 seconds, which was the first time we had that we found in the first problem. And the other one is 0.743 seconds. So we have to use that one for this problem as it's the other time. And then we just plug that into d equals vt along with the horizontal velocity, which is 11.6 meters per second. And you get out 8.62 meters.
Good. Could you scroll up to part A just for a second? Okay, thanks. You can scroll back down. I just wanted to check something. So
Okay.
that way, if anyone's still looking at part C. So we'll keep it on the screen for a few more seconds. Anybody have any questions about part A or B or C for number 1? You can just unmute and chime in if you have a question. All right. Yeah, I don't think I have any questions either. I want to make sure you understand what's going on in part C. A lot of times students get pretty confused about this kind of a question, but it's a pretty common question. They did a great job of solving it and did a great job of explaining how they solved it. But I just want to actually make sure you understand the question well. So let me, if no one else needs this screen.
I can draw on it if you want.
Okay,
Or,
sure.
yeah.
That's what I was gonna see if you had drawn anything on the picture up there.
No,
So,
but yeah, if you have your floor and the building, then there's one angle that goes like that, and it hasn't reached the peak yet. And then there's another angle that comes up and over and reaches the same point. And so we already found, I believe, this top one. And so it was asking for what is this bottom one, I think. No, that's not right.
that's another kind of question you could be asked, what the different angle is. This case, they're keeping it at the same angle.
Oh yeah, so it can come up and over like that, or it can just come up, and they want to know what this angle was, or distance.
Yeah, yeah. So that's exactly right. So it's just a matter of recognizing that it's a parabola. And so the parabola has two heights on either side of the apex that are equal. And in the first scenario, you're just looking at, like Ethan said, the height after it's already reached the apex and is on the way down. And then in part C, you're finding that same height that it would, when it would reach that same height, but still on its way up. So yeah, good. All right, let's move on to number 2, group 2.
Okay, can you see it?
Mhm.
Okay. So for part A, we know our initial velocity of 25 and our angle to be 50 degrees. So using those, we can find our horizontal and vertical initial velocities using cosine and sine. So for our horizontal initial velocity, we got it to be 16.1 meters per second, and then our vertical to be 19.2 meters per second. So I used the second kinematics equation because we knew that our change in y is also 0 because it goes up and then falls back down, so its displacement is 0. So plug that into the second kinematics equation using that displacement and then the vertical initial velocity and gravity. So we got time to be 3.84 seconds. And then we can just use the first half of the second kinematics equation to find the change in x. So we used the initial horizontal velocity and then the time that we found, and we got it to be 63 meters. And then for part B, it's asking for the maximum height. So we only use half of the time that we found in part A because it's only half of its journey up. So basically the same thing as A, we use the second kinematics equation, but now we used the vertical initial velocity and then gravity and then half of our time, and we got it to be 19 meters.
If we can pause there just for a second and see if anybody has any questions. I know some people may still be trying to kind of digest, especially if they did it a different way. For instance, for part B, I used the third kinematics equation we learned, and then it didn't rely on time. So some students may be seeing this particular pathway for the first time. So any questions? All right, we'll keep moving.
So for the motion map, we have, because there's no air resistance or drag, the horizontal velocity stays constant, and that's why it's like the parabola is even. Then there's the initial vertical velocity that is affected by the acceleration due to gravity, which is negative 9.8. And so it is decreasing in speed in the first half, and then it increases as it's going downward.
And then for D, for the what factors could be adjusted, so if the angle was changed to 45, then that would maximize the range. And then also if you increase the initial velocity, that would also do that. And then for E, to maximize the vertical height, increase the angle to 90. And then you could also increase the initial velocity again.
Good. So yeah, I would make sure on that last one, you said it verbally, just making sure no one missed that you do mention the angle. So like in D, mentioning the angle of 45, and in E, mentioning the angle of 90. And in both cases, as you mentioned, increasing the velocity would help it as well. For part C, it asks you to list the velocity vectors, which we see the actual vectors, which are the angled ones, and then we see the components, the horizontal and vertical components. How would the acceleration vector be drawn? What would the acceleration vector look like?
It'd probably be a arrow pointing downward that's constant on all of them.
Good. And because it's a little hard, you've got these velocity components going down on the second half of the parabola. So if you're drawing the acceleration as well, then there's kind of overlap. You can just draw off to the side like the letter A for acceleration and a downward arrow and just say acceleration is constant. So, or just draw a downward arrow with an, and then put A equals negative 9.8 meters per second or squared or something like that, so that they can recognize, you know, it's downward and that it's constant. If you use a different color ink or a dashed line or something, you might be able to draw it on all the dots. But it starts getting a little confusing on the right side of the parabola when you've got two different downward arrows. So, questions? All right, group 3, number 3.
So for number 3, we first found both the initial velocity for y and x, and from there we wanted to find the time, but first we needed to find, we used the third kinematics equation to find the final velocity of y, which we got as 4.88 meters per second. And then we used that to plug into the first kinematics equation to get the time that it took from the ball to fall from the sphere to fall from the top of the ramp to the ground. And using that first kinematics equation, we got 0.55 seconds. And we also, I forgot to mention this too, we changed the final velocity to negative since it's falling downwards. And then from there, we just use, because now we have the time of how long it took to fall to the ground, we use velocity times time of x to get 0.77 meters.
Good. I think this is the first time I've seen a group use this strategy, but it works well. Most of the groups that I've seen explain it use the second kinematics equation we learned to find the time. The tricky part of doing that is that you end up getting a quadratic equation. So you have to use the quadratic formula or the solver. If you have a CAS, TI, Inspire, you can use the solver function there. But this way you avoid having to use the quadratic formula because you can, it's a two-step problem this way instead of one, but to get the time, but it might still be faster if you don't have to worry about the quadratic formula and you don't have a CAS to use the solver function. So any questions on number 3? All right, group 4, number 4.
Okay, well, let me just share my screen really quickly. This one? No. Yes. Okie dokie. Okay. Now, the picture is not necessarily the greatest. So you just kind of start off by doing, sine and cosine. I didn't really write it there like I should have, but we did the sine of 15 times 1.5, which is how we got the, the bottom, I believe. The opposite, sorry. And then we did tangent of the opposite to get the bottom. And then so that's basically how we got the 3.88 and the 1.45 in those positions. And then we plugged it into the second kinematics equation and then got the time. And then
yeah, that's, you just got, once you get time, then all you do is rate equals distance times time, and then you plug those and you plug in 0.391 and 1.45, and then the final distance is 0.57 meters.
Yep.
All right, any questions about number 4? Can you put that back up again for a second?
My bad, I forgot about that.
Just in case people are still looking.
Yeah.
Did you guys use the quadratic formula or did you use the solve function on your calculator? How did you get that 0.39?
Yeah,
The function
solve
Okay.
on Aiden.
a little easier.
Or
Mhm.
Andy, sorry. Yeah. It's just like I would have used it, but it's only on the cast, right?
Yeah.
Okay.
All right, good. So any questions? Sorry, I kind of interrupted there. All right, thank you, gentlemen. Thank you all four groups for your explanations. Let me show you a little bit about that solver function. If you haven't used it, but you do have a CAS calculator, it's this second row. I'm going to talk about that sine of 45 here in a minute, but so you can, there's somewhere in the menu, and I forget where it is. I just always type the word solve in. To me, it's faster to type it in than to try to remember which menu I find it in. But you could just use the keyboard down here and type in solve and then parentheses. And then this is the equation they had. It was falling 0.9 meters. The vertical component of the velocity they found using trig was negative 0.388. Since it was coming off a downward slope, it would have a negative downward or a downward or negative vertical velocity. And then that's just your 1/2 and the acceleration due to gravity. And so there's the equation. It has to be an equation. It can't be an expression. So there has to be an equal sign. And then after the equation, you put a comma and then the variable you want it to solve for. So since most of the time you see these, you'll see x, but since I used t in my equation, I just said solve for t. And you can use whatever variable you want. And then, yeah, those are the two answers you get, but this one here is negative and you can't go back in time. So the positive one is the one you should choose. So if you haven't used that solve function on your TI Inspire, if you have the CAS, you can see over here on my calculator here, it says it's the CAS version. That can be pretty helpful. All right, let me go ahead and go to number 5, and I'll do these last few here. Oh, this is another way you could show, it seems a little unnecessary, but here on the key, they're showing just what they did on that for the actual acceleration, or sorry, the actual velocities plus the components. And then they just did the same thing. They like mirror imaged it for the acceleration. And then this is the number 5. Suppose a water polo player could impart a maximum velocity of 25 meters per second to a ball, and that this velocity could be oriented at an angle relative to the surface of the water. In order for the ball to travel as far as possible, achieve maximum range, at what angle above the water should the player throw the ball? Justify your answer both mathematically and conceptually. So this is mostly conceptual, but I integrated a little bit of math. I edited it just slightly to add some math into this paragraph. And mainly the reason I wrote it as a paragraph is I wanted to remind you that we haven't really done any of that yet, and there won't be one on this Friday's or Thursday's test for you. But on the exam, there's always one FRQ that asks you or requires you to write a paragraph length response. And this could be an example where they might ask that. And so I just thought, well, I'll give them an example, show them what a paragraph looks like. I mean, you know what a paragraph looks like, but show what a paragraph length response would look like for a free response question. So this would be how you could answer this with both a little bit of conceptual and a little bit of math integrated into the paragraph. A launch angle of 45 degrees will maximize the range. So you're first off just stating your claim. Range depends on two variables, the horizontal component of velocity, for example, the number of meters traveled horizontally each second, and the time during which the sphere is in the air. For example, how many seconds the object has to travel horizontally. Assuming the launch height and gravitational force field are held constant, time in the air can be increased by increasing the upward component of velocity, in other words, the y component. If the sphere is launched at 45 degrees, the x and y components of the velocity will be equal. And here's a little bit of the math. The sine of 45 degrees and the cosine of 45 degrees both equal 0.707, or the square root of 2 divided by 2. This strikes a balance between maximizing horizontal velocity and maximizing time in the air. So you've said you made your claim, you've explained your rationale, You're given the evidence basically for how you can make that claim. And you've included just enough math to explain that the sine of 45 and the cosine of 45 give you the same value. And that's mathematically why they would contribute equally to the flight of the object. Now, you could go through a much more detailed mathematic breakdown, which is what they also include here. And I'm not going to go through this entirely, but I do like the way they've separated the x component variables and the y component variables, and then the x component constant velocity portion and the y component constant acceleration vertical portion. And then they just did some substitution to sort of prove why it would work. I don't really think you need to go quite that far. I think you can just show that the sine and cosine of 45 are both equal, and therefore you'd be maximizing both. It makes enough logical sense to me mathematically, but they did go a little bit further. So if you're curious about that, there are some other ways you could try to just mathematically break it down. But I think more often they would probably ask you in this kind of a question to give a paragraph length response. So I wanted you to see that too. Any questions on number 5? All right, number 6. Frustrated with history. You never get frustrated with physics. Hopefully you don't get frustrated with history either. You open the second-story classroom window, and to the horror of your teacher, but to the secret delight of your classmates, you violently hurl your history book out the window with a velocity of 18 meters per second at an angle of 35 degrees above the horizontal. If the launch point is 6 meters above the ground, how far from the building will the book hit the lawn? So on the left here is a series of variables. The delta y is negative 6 meters. It's going to end up 6 meters below where it started. It doesn't matter that it actually went to a higher peak first, right? Displacement is final position minus initial position. So its displacement will be negative 6 meters. Its initial vertical velocity is 10.3 meters per second, and the initial horizontal is 14.7. And then you can see here just using sine and cosine to find those values. And then they used negative 10 for their value for g. And we need to find, the question says how far from the building will the book hit the lawn? But in order to find that horizontal displacement, we need to find the time of flight. So we need both the time and then after that, the horizontal displacement. So the way they've set it up, they've used the second kinematics equation that we learned, and they're focusing on it vertically. You can tell they're focusing on it vertically because it has delta y as their displacement and vyi as their initial vertical velocity. The delta y is negative 6. It's falling 6 meters from where it started. The initial velocity is positive 10.3 because the angle was 35 degrees above the horizontal. So it actually had an initial vertical velocity that was upward. And then the acceleration due to gravity, they've used negative 10 here. Now, this is a quadratic equation. So you could put it into the TI Inspire and have it solved. You could use the quadratic formula. You could factor it. But somehow you need to come up with the 2 values for time. And for this one, the positive value is 2.53 seconds. So that's the time of flight. Once you know the time of flight, you can use for the horizontal. Horizontal displacement is basically VOT in the horizontal plane. The 1/2 AT squared doesn't matter because there is no acceleration for horizontal movement in this case since we're ignoring air resistance. So the displacement will be the 14.7 meters per second, which we found up here using trig as the horizontal component to the velocity, and the 2.53 seconds that we just found using the second kinematics equation. And multiplying those, we would find a horizontal displacement of 37 meters. If we're thinking about sig figs here, this time really should be 2 because the 6 meters was 2. So that would be 2.5, and then this would be 37. So they've rounded their final answer to the 2 sig figs based on 6 meters, but they haven't rounded intermittently in between. College Board actually recommends that you don't round until your final answer unless there's specific addition versus multiplication division steps within an equation. So this basically, I mean, yes, there are some addition steps, but they end up being all able to be resolved independently. So questions about number 6? All right. Number 7. A ball is thrown straight upward and returns to the thrower's hand after 3 seconds in the air. A second ball is thrown at an angle of 30 degrees with horizontal. At what speed must the second ball be thrown so that it reaches the same height as the one thrown vertically? So if we think about this conceptually, if I throw it straight into the air, it'll go to a certain height. If I throw it at that same speed, but I throw it at an angle, it's definitely not going to go that high. If I want it to go that high at an angle, I'm going to have to throw it much faster to get it to reach that same peak. So here on the left, they've started with saying, okay, let's look at the first scenario, throwing it straight up. We're going to say positive is upward. It goes straight up and comes straight back down. So the delta y is 0 meters. It has a 0 displacement vertically, and it has an acceleration of -10. You could use 9.8. And the time of flight in this first scenario when it was thrown straight up is 3 seconds. So that's what they know about the first scenario. Now down here is the second scenario. They know that it's going to be thrown at 30 degrees, and they need to know this vertical velocity to figure out what the actual velocity at the angle would be. And this vertical velocity, you can see here in the sentence, for the ball thrown at an angle to get to the same height, it has to have the same initial vertical velocity as scenario 1. So the reason they know it has to be 15 is based on the math right here. They use this initial scenario, the displacement equals VOT plus 1/2 AT squared. In the initial straight up and down scenario, the displacement is 0, time is 3 seconds, acceleration is -10, and they solved for the initial velocity. So in that first scenario, throwing it straight up, it was thrown straight up at 15 meters per second. At this angle, if you throw it at 15 meters per second at that angle, it won't go as high. So your vertical component has to be 15 meters per second to reach the same height. And if you know the vertical is 15 and you know the angle is 30, you're trying to find the hypotenuse. You're trying to find what you would actually throw it at. And the sine of that 30 would be opposite over hypotenuse. So solving for the hypotenuse would be opposite over sine of 30. And you would find you'd have to throw it at 30 meters per second in order to get it to the same height if you only launched it at a 30-degree angle or threw it at a 30-degree angle. Questions on number 7?
I just did I used VVAT, and then because my final velocity was 0 because it would go to the peak for the height, and then I was solving for the initial and then acceleration and just gravity, and then the time would just be 3 seconds because in the problem.
Mhm.
That's like all I did, and is that okay? And then I just
So-
solved for it.
So did you get the 15 meters per second or did,
No, I didn't use the 15.
okay. So you did, so explain to me your method again.
I just used VVAT, and then so for final velocity, it was 0 because I'd be to the peak.
Mm-hmm.
And then I'm solving for the initial velocity. And then the acceleration is -9.8 because gravity, and then time is 3 because it would be in the air for the same time as in the problem. And then I just solved for the initial velocity and I got the answer.
You got 30?
Yeah.
So you're going from, oh, the 3 seconds. So you got double the answer.
Oh, I did? I'm not entirely sure what I did.
Yeah. So the way you solved it, 3 seconds is the entire flight, and you used it as that's how long it would take to get to the peak.
Oh, okay. Oh, yeah, it should have been 1.5.
Yeah.
Okay.
So what you would have been solving for was the initial velocity. And so basically this step here that's using the second kinematics equation, you just use the first kinematics equation to find the same thing.
Yeah.
Yeah, and that would be fine, but you would still have to go through this step. It happens to work out because of the 30-degree angle, the way you did it. But if it was a different angle, I think you ended up sort of luckily getting the right numeric answer just because of the angle that was chosen. Yeah.
Okay.
Yeah.
Could you, so we know that the first ball. Oh wait, never mind.
Any other questions? This is the trickiest one in terms of just putting a little twist on the question. All right. So real quick then, just to wrap things up, let me go back to the PowerPoint here. So reminders again, worksheet 3, make sure you're getting that submitted on Access tonight for your completion/participation grade. Remote students, if you're watching this video later, don't forget you need to sign up to take the Unit 4 test either Wednesday morning at 7 a.m., Thursday afternoon at 4 p.m., or Friday afternoon at 4 p.m. Let me know. For the rest of you, you'll just be taking it in class on Thursday and Friday for A Day and B Day for Unit 4 test. And then the format of the test, 10 multiple choice questions, 2 points each. That's been pretty standard the last couple of tests. There are 4 FRQs this time, but I think they're a little less time consuming, and 2 of them are pretty short. There's a middle length one as well, and so you can kind of see the order. There's a short one, then a medium one, then a short one, then a long one. Even though there's 4 though, I think you should still be able to get these done in about the same amount of time because they're not quite as in-depth, and we're not really covering as broad of a number of topics. It's just projectile motion. There's not a lot of different ways to test projectile motion. So I think you'll actually find this test, if you understand what we've been doing and the trig and everything makes sense to you, I think you may find this test slightly easier than the last one. Still challenging, but yeah, so still prepare well. And then all the things below, those are all the things I've said before. I've shown you, I think this is the 3rd time now. These are the things you could use to review. But I would say that other than the practice problems there, the 3rd bullet point, I think the Unit 4 on positive physics, going through those examples on projectile motion, and then watching the videos and going through the multiple choice questions on the AP Classroom. If you go to the AP Classroom on kind of the home page, you'll see the daily videos broken down by topic. And then if you go to the Assessments tab, on the Assessments tab is where you find the questions. And there's a topic 1-1 questions and a topic 1-2 questions, and then a multiple choice part A or something like that. So those would be the questions you'd have available to just practice. And all the topic questions and multiple choice questions in that assessment tab are multiple choice format. So that would help you prepare for the multiple choice part of the test on Friday, Thursday and Friday. Thursday for you guys. Any questions about how to review or what to review? All right. So we have what, about 15 minutes left. So if you have questions, feel free to stick around. I'll hang out and answer any questions, or if you don't have questions, you're welcome to be dismissed a little bit early and just start on your review. Don't forget to upload that worksheet 3. You could use the time to do that as well. Get that up on Access. But otherwise, if I don't see you with questions here in the next few minutes, I'll see you next time, and have a great rest of your day.
Thank you.
Thank you.
Thank you. See ya.
See you.